So over the next hour, we'll split into two, as Tim has suggested. So I'll begin by talking through the design engineering behind the new roof to the Olympic Stadium, and pass over to Chris to cover the erection engineering. My slides will be a little bit more of the what and why, and talk you through the process with a little bit of how later. Chris will probably deal a little bit more in details of how everything was erected. So I said there wasn't so many hows. My first slide is a question. So how do you double the size of the Olympic Stadium roof? On its own, that's a fairly challenging question and challenge. However, you'll soon see that it wasn't just the question or the answer that was difficult. The question proved to be a little more convoluted than that along the way. I wanted to bring you back to the heady days of the Olympics first. So it's 2012, and everyone's very excited by what the UK have been able to produce and deliver. I personally it was a real pleasure and pride to be able to look at the Olympic Stadium being used and know that we had been part of that. And you probably also know that the original brief of the stadium, it was an Olympic Stadium. It was a summer event stadium. The brief was that we would have a summer event where 80,000 people would be able to come and watch the Olympics. You would then go into legacy mode beyond, where 25,000 people would be able to watch further athletics events. It was to be delivered as an athletic stadium going into the future after being reduced in size to 25,000 people. So the response to that design brief was a stadium that looked very much like this. So down in the lower bowl, we had 25,000 seats. They were permanent. They were going to stay there for the full period of the stadium's life. We then had 55,000 seats in a dismantleable upper bowl. And there were all sorts of thoughts about passing the upper bowl on to the next Olympics and letting it just pass around the world as Olympics went on. Obviously, that hasn't happened. So, interesting, we're going to talk about the roof today. Now, the purpose of the roof wasn't to keep these guys dry. It was meant to be a summer event. The purpose of the roof primarily was to ensure that wind speeds within the athletics stadium were at a level that meant that when Usain Bolt broke the world record or whatever he was going to do, it stood. It wasn't disqualified for being over the 0.2 limit. So we had a stadium like that to begin with, but even before this was in use, so even before the games, the public and sort of political machinations were moving at such a pace that actually people were beginning to say, you know what, we quite like this. It's a great stadium. We don't like the idea of building something that holds 80,000 people and then knocking it down. Unfortunately, or perhaps fortunately, depending which way you look at it, there is only one way in the UK to make such a stadium not to be a white elephant, and that's to say that Premiership football will be hosted there and find a tenant to play Premiership football there. And if you're going to try and host Premiership football, you need to cover all the seats, which is where our story starts. So even before the Olympics were complete, we were beginning to look at options for covering all the seats in the stadium as it stood. And this is where the story begins. So what we have here is saying, well, okay, we had an original roof, which was a tension cable net system. Let's see how far we can push that. So we're saying we've got existing compression truss. We don't want to do too much to that, maybe a bit of strengthening. But how far can we extend this cable net? Can we cover all the seats? And although the compression truss at this stage was beginning to creak a little bit, it was possible to begin to stretch it right out to here. Some of the lights came down onto the front. Some of the structure behind the lights was dropped off, so weights were maybe a little bit smaller. And one of the key points to highlight here is that we still have a fabric roof. So what we end up having at this stage is something which is really it's an extension of the original. It's all following the same principles. It's a cable net system. It's a fabric roof, therefore it's lightweight. So primarily the cable net system is its pre-stress is resisting upwards loads from wind, downwards loads from a bit of wind or snow, but the dead load is kept to an absolute minimum. Now, as we move forward, you'll see that all changed. And one of the first reasons why that had to change was, well, the whole political landscape keeps moving forward, and Spurs and West Ham fight it out for the tenancy rights, and West Ham eventually come out on top on that. Alongside that, the public are beginning to realise, oh, right, we're going to play football here. Great, it's still we like the fact it's still an athletics track. That's right and proper. But the message from all around the world is that you can't play football with an athletics track. That just doesn't work. And particularly West Ham supporters are saying we don't want a stadium that loses its atmosphere. So to create a stadium where football can be played, you have to start thinking about moving seats. So rather than suddenly having a situation where we just had to cover all the existing seats, we now have a situation where not only we have to cover all the existing, but we also have to cover seats that have now moved in all the way across the athletics track. And so the roof's getting bigger and bigger and bigger. Add to that a requirement to host concerts, other events of that nature, and suddenly rather than having a lightweight roof, there's a quest. Well, can we begin to insulate it? Can we begin to acoustically insulate the stadium and prevent some noise spill out? So, having moved to a much longer span, we're also now adding a lot of weight into the roof. So it's all the original premise of can we double the size has moved on and on and on. And we begin to then see a diagram like this. It's not 34 metres like it was originally. It's not even sort of the 55 metres that was once covered. We're now talking about maximum cantilevers, although cantilever obviously isn't quite the right word, of around 81 metres, which is getting beyond anything that perhaps anyone had considered before. So it was a challenge. And this is where we obviously had to get our scratching our heads, thinking caps on how can we do this? And again, this is where we had to engage with the client. What is it everyone wants? And there are various political motivations behind a lot of things. There are obviously cost motivations behind a lot of the decisions that get made. So we want to present a whole series of options and leave those decisions in the hands of those who can make them. So we take you over to this right-hand side. There are perhaps the simplest way forward to say, look, we've reached the end of what the existing structure can do. The existing compression truss is no longer able to cope with the situation we're in. We're going to move away from using the existing, and we're going to knock it down. We're going to rebuild, and we can rebuild in whatever way seems most appropriate. It can be a cable net system, or it could be a bending frame system. There's a lot of engineering wisdom possibly behind that, but there's also the idea was to say we want to keep this stadium. So in the public's mind, the stadium was the compression truss and the diagonal steel columns. That's what they saw when they looked at the stadium from externally, and to knock that down and rebuild would have gone cut against the grain of everything that was trying to be achieved. So that side begins to get ruled out. Over the other side, we've got options where we keep the existing truss, but do a lot of strengthening to it. Compression cords probably need to be have elements welded to them to stiffen them up. A lot of the connections will definitely need strengthened. The lacing members within the cord may need replaced. So we could go right across to this and try and create a cable net with a much stronger compression truss. Or there's a whole series of options in the middle where we reuse the existing compression truss but have a second little roof, or we add it's hard to tell in this one, but there's an existing compression truss with a further compression ring behind it. Something completely different where we have a guide mast supporting an inner piece of roof. Or these two options, and this is where we're going to start concentrating, where rather than telling ourselves that we've reached the limit of what the compression truss can do, we start to say, well, we've only reached its limit with regard to horizontal loads. Is there a way that we can reuse the capacity of the compression truss with regard to horizontal loads and carry the greater vertical loads that are now appearing? So that's where we're going to move towards. Just quickly, it was absolutely right at this stage that a whole lot of options were scored with regard to a whole series of parameters. Some scored very badly, others, not the solutions we arrived at, scored pretty well. But again, obviously, weren't particularly well favoured with regard to the idea of keeping the original. Whereas this, as in coming to a gravity-stressed cable net system, began to score very highly indeed, with structural design, complexity being the only point at which it dropped down on. We couldn't let that be the reason we didn't do it. So, as I say, we created a chart, presented that to the client, and it became fairly clear alongside Popular Sewer, the architects, that we could work together towards the solution that everyone wanted through a gravity-stressed cable net system. So I think it is the right moment to stop the story and just explain briefly what we mean by a gravity-stressed cable net system. Now, I think most of you will be fairly comfortable with the fairly ubiquitous cable net roof system where it is analogous to a bicycle wheel. So what we have is a compression truss that is like the rim, a tension ring which acts like the hub, and a whole series of cables acting as the spokes, putting compression into the compression ring and tension into the tension ring. Now, the whole reason behind that is obviously to carry vertical load at the end of the day. It's a spanning system, so it's to carry vertical load, and the way it can is by resisting uplift within the pre-stress when the cable's running upwards, and resist downloads by that same pre-stress in that system. So what you're doing is introducing pre-stress horizontally in order to cope with vertical loads eventually that pre-stress. And it means the cables, to start again, the cables are inclined upwards and downwards in order to carry those loads. The move that we then decided upon was that rather than having this system of cables, which I think in the next slide we'll move on to be slightly clearer. So in the original, we had this system where we had a downwards cable pre-stressed against an upwards running cable, and that meant that upwards and downwards loads could be carried, balanced by the pre-stress. By dropping the whole system down, we suddenly have a situation where not only are both cables resisting gravity vertical loads, but they're also at an inclination where they're doing that more efficiently. So the horizontal loads required in this system to carry gravity loads to begin with are equivalent to the horizontal loads in the previous system. What we're also then finding is, well, what do you do about uplift? And you've got to get to a state where the gravity loads are sufficient to resist the uplift in the wind condition, which is where we've moved to. And we'll go quickly back to that and just say, well, it's a bit like we've merged the bicycle wheel scenario with either a cable stay bridge or a suspension bridge type situation where all the pre-stress is being created by the gravity loads. You could probably ask yourself the question, is that a pre-stress system? And I think you probably have to say it is, because in the equilibrium state, the gravity is causing the cables to go into stress. So any move from the equilibrium state under any applied loads is acting within the pre-stress of the system. And so this is what we ended up with. It's obviously very significantly longer, very significantly heavier, and but by dropping the whole system down and having both cables acting against gravity and removing the pre-stress that was required to act against upwards and downwards loads, we've reduced the horizontal loads back to a similar situation. What you probably have worked out is that although we've reduced the horizontal loads, the vertical loads are still vastly increased from the original. And what we found, and what Chris will describe later, is that although we managed to ensure that none of the members within the compression truss needed to be changed or strengthened, we did require almost all of the columns to be replaced. And so part of the whole construction process was to swap those columns out individually, which is quite an entertaining little bit of work as well. I probably ought to say at this stage, and Chris will say later, that although all the members were satisfactory and didn't require strengthening, a number of the connections did require strengthening, and that work was also done. And what we're left with? Well, we're left with a system where it's quite a clear hierarchy. We've got a set of existing compression truss and columns, although the columns aren't existing. That has a series of a cable net applied to it. That cable net is stressed into position by a steel rafter system. Now, at this stage in the design process, it's important to note that we had intentionally ensured that the steel rafter system purely spanned radially and provided a set of dead loads to the cable net system. It wasn't trying to act structurally on its own, apart from spanning. And in order to make that happen, it took on a folded shape. On top of that, with a series of purlins, and you can begin to see the folded shape of the roof, and finally the cladding. So, if I then move on, that's where we had got to, and we were all very happy with this. It was a nice roof. It fitted with what Populous were aiming for. We were comfortable we could make it work with the existing compression truss. This was about April 2013, and so on this timeline, we've obviously stripped all the way through the Olympics. We're just coming up to the last event that would be held before the chosen contractor would come and start dismantling and converting the stadium. So we're getting close, and the contractor comes on board. We get a full costing done of the situation, and there's an affordability issue. So a lot of people have to, again, scratch their heads very hard and look back at what we can do. And the outcome was to look at what we had and say, well, actually, there are some complications here. The idea of trying to ensure that the rafters don't pick up any load, or the roof, the steel roof itself, doesn't pick up any additional sort of parasitic loads, maybe isn't quite the right option. It's given us a lot of complexity in the folds within the original roof. So what can we do to simplify that? And the answer came in the form of a flat front roof. It's actually quite conic in its shape, and so it becomes a structural element on its own. So it begins to bring in some efficiencies in those elements. They're actually doing more than just spanning radially. We also then introduced a separation, and this is quite an interesting item. It meant that the front roof could act in that sort of diaphragm way as a cone, but the rear roof remained simple. So the rear roof, it remains just sitting and loading the cable net system on its own, and you'll see through the diagrams and through the construction sequence that worked out very well. And it also meant so at this point we were having quite serious difficulties with the connection between front and back roof. The forces being generated at that point were substantial. That was causing a significant connection to be required, and that was one of the elements that was pushing costs right up. So by flattening out this roof, beginning to let it act in a structural fashion, and separating it from the back, suddenly we were beginning to get the steel tonnages a little bit lower, and also took a bit of complexity out of the whole system. And contractors were scared of complexity, so that's part of the reason why the costs were high in the first place. So where have we got to then? So as you can see, we've got the moving seats, meaning we're now covering all of those as well. That's moved out right out to there. And the system has become really quite an interesting one when you sort of look back and see what has been created. We have our, I suppose, almost suspension bridge cable that runs to the tension ring, around the tension ring and back up the other side. But sitting on it, we have this almost arch compression system from the front roof. So these struts, the lighting tower struts, and the rafters, as well as the rings with it that join the rafters together, are all acting as a compression system. So they obviously react against the cables below, causing a little extra tension into the tension ring. But we're beginning to get some structural capacity from those, and some ability to span, which just assists the whole roof and brings some of our member sizes down. And this is the point where either you'll decide that was the interesting bit and you'll go to sleep for a bit, or you've been holding out for how did they do it? How did they do the analysis? In which case you might pick up. So it is obviously a very complex roof still. It's a system which is absolutely interacting in all sorts of ways with itself. It's not something you can you sit and take a cross section and design fully from that. It's interesting to be able to draw the cross section is important, and to draw the structural system as simply as that is important. But to get to the really to the bottom of, does this work? Does it stand up under snow loads, wind loads, and everything else? We've got to create a complex model, and that complexity, we've got to bring our architect along with us. So one of the primary tools that's made, I think, this possible to the extent that it is, and I'm not sure that some of you will be familiar with parametric geometric modelling. This happens to be Grasshopper, and there are other ways to do the same. But what this scripting allows us to do is control and reproduce full models, geometric models, from a series of inputs. So a few slider bars, a definition of the level of the drip line, a definition of the level of the cable net, how many purlins you want. We're able to tweak the input, and a whole new stadium geometry is produced. Now, without that, the level of iteration that we've been able to go through would have been just impossible, and we would have been fighting against the architect, fighting against anyone who wanted to change anything, to say no, it has to be what it is. So by beginning to allow ourselves this kind of control over geometry, it allows the freedom to make those changes as the design develops. So that's not a model in itself. We need to take that sort of clever parametric geometry modeling, add to it a whole lot of input data. This is all about member sizing, loading, number of load cases, all stored within within Excel sheets, and those are then combined into a single analysis model. What that allows us to do is just batch process that whole system. So we can make the small change in the geometry and rerun in a day's work rather than 3 weeks' work. We can make the small change to the loading, rerun. We can make small change to either. So that we've got the control to make those changes and allow iteration to happen, which again allows us to create more efficiently sized members and rerun the iteration. We finished on model 103. So we've run this full set of load cases at least 103 times and more. This is a slightly complex slide, but it's the reason I put it up is that there's we're obviously working within a sort of a technical environment, and we're trying to solve some technical problems. We're also working within a design environment with regard to an architect. So we go to meetings, share geometry files with them, and they think, yep, that's perfect. That gives us the drip line exactly where we wanted it. It gives us the tension ring at a level that doesn't interrupt sight lines. So if we take that geometry and go away and apply loads to it, unfortunately, and turn gravity on, unfortunately it moves, which is unfortunate because it's a dynamic system that moves by up to probably up to a meter under its own self weight. So we have to somehow get to a point where our model is correct in the unstressed state, or is incorrect in the unstressed state, the gravity is added, and then it gets to the point where we've agreed that the architect wanted it. And that's a relatively challenging thing to do, and the reason for this slide is just to highlight how that works. So eventually, this is the final model, and it's the final equilibrium state, but we're working back to get to that point. So what we start with is by adding all the major dead load, or taking a model of the major dead load pinned in all its primary support positions, and out of that model, we're able to create a surcharge set of loads. And for actually reasons of trying to match the erection procedure as closely as possible, and this is where we sort of begin to tie in with Chris, we've simply taken the vertical elements of that load, because the erection sequence would eventually use pure tie downs. So using that vertical set of gravity loads, we load them onto a cable net, which again this time is pinned at its perimeter, so no compression truss in place, and is fully rigid with its cables, so the cables can't stretch. And from that we get a series of cable forces that would carry the dead loads if the geometry was as we want it to be. We sort of store that for the time being, and we take our compression truss, and rather than it being in its fabricated state, we allow it to relax into its equilibrium state without any load on it. We then take the cable stresses that we had just developed from earlier and apply those to the compression truss. So now we've got a compression truss which is in its equilibrium state, its final condition. So it's got all the loads that will eventually be applied to it for the equilibrium state, and it's moved into that position. It's only then that we can It's only then that we can turn on the cables with the correct stiffnesses at the same time as applying the surcharge loads, and everything goes back to the right position. And we then swap the surcharge loads for the actual rail steel, and again, we don't actually change. The geometry doesn't change significantly at that point, which is exactly sort of what we're aiming for. So it's a complex procedure to go through each time, but without it, we just don't have control of the final geometry, and therefore don't have the coordination with the architect that is required. I'll flick through these very quickly, but this is just some of the same things mentioned again. So we have a process, a very well-defined process, where we have a lot of input elements to do with geometry and model definition. That passes through an analysis model. We happen to use GSA, and then we throw it into a post-processing set of spreadsheets. Now, that either comes up with the answer, or it passes everything back for an iteration. And obviously, more often than not, it passes everything back for an iteration. And we work through the process again and again. That's just the same thing in images. Now, loading was absolutely key to this. In order to make the compression truss work, we were, as I said earlier, that we managed to keep the horizontal loads to pretty much what they were previously. That's not really true. We were working. It's working harder than it was previously. We kept them within limits that were achievable. And the only way to keep them limits that were achievable was to be very careful with loading. First place to be careful, obviously, is wind. So this is the wind tunnel model. we used BMT to produce that and test it for a whole series of obviously wind directions. Came up with accurate plots of wind pressures that we were able to feed directly into our design. We also then used, due to the nature of the situation as being dynamic, you couldn't, it wasn't just a matter of saying here's a rigid system, let's apply wood, put it in the wind tunnel, get the static pressures, plug it into our analysis. I won't go into it now, and I probably wouldn't be able to go into it because I had friends doing this for me. But that conversion of sort of the dynamic and the aeroelastic effects on the structure, just looking at those, the interaction between mode shapes of the structure and the wind pressures, meant that the dynamic pressures that would have been required are then converted to an equivalent static load for our model, and that's the load case we used. It's also needs to be highlighted that there was a whole lot of separate studies into various wind-induced vibrations, whether it's on cables or on the front edge, for flutter and the rest. So we can, I won't go into that today, but there was a whole series of studies there. The other thing to note is that there's a lot of steel up here. Actually, we do end up with a situation where partly the major steel structural elements, but also everything else, so gantries, lights, gantries inside the lighting towers. There's a lot of stuff up there which, if we make estimates at the sort of the usual structural engineer's estimate of dead load, we would have been way over. It would have been fairly easy very early on to say, the gantries are a kilonewton a meter, 2 kilonewtons a meter, whatever the right number is, and but come back. But we said, well, that's actually not good enough for us here. Not only because if we overestimate the dead load, we will we'll kill our compression truss, but also if we overestimate the dead load, our analysis model will be wrong. It'll have deflected too far, and it'll be a completely different shape, and it might be carrying loads in a more effective way than it would otherwise be. So, making sure that we had a really tight feel for dead load of elements like gantries, purlins, and the like was key. We always apply, obviously, a code-based 1.4, 1.35 to all our dead load elements, and very wisely most of the time. As this was a fabricated steel structure with fabricated steel elements, we were very aware that we actually knew we knew how heavy that steel was. The fabricated element, we had a Tekla model produced by the contractor, and we had our own modelling. We were pretty confident to within a 2% variance range that our fabricated steel elements at least were going to be the right weight. Now that whole 1.4 factor isn't all to do with dead load variance. So we investigated and split up that dead load safety factor into how much is to do with analysis modelling error, how much is to do with tolerance, how much is to do with variance in the dead load. And it became clear that it was possible to, with confidence that we knew the weight of particularly the rafters, we would be able to apply a lower factor to those particular elements. And that was all part of it was absolutely a necessity in order to make the compression truss work without serious strengthening of members. So part of the system was we set the dead load safety factor on the rafters to 1.2. That on its own was all very good, but we need confidence in that. So we had to ask the contractor, or at least put in the specifications, that had to be verified. So all the rafters, the lighting towers were weighed on the crane before they went up, and just to show that the Tekla model, when taken through to a total weight, was correct. And that's worked very well. We've been able to show that actually the variance in weight of those is minimal, and the 1.2 factor was appropriate. The other point at which it gets awkward to define dead load and becomes a bit difficult is these connections. We weren't in control of connection design. We give indicative connection designs, and then contractor, the steel fabricator hires developed them. So there was a very sort of close link there where we created an analysis, or so we created an estimate of what that connection rate would be. That was in our analysis model. We then passed it on to hairs. They had to work within that, and the final design. Then we updated our model to show exactly how heavy each of these connections were. And so that was one particular connection. There's another, and this was designed by Pfeiffer, who developed the cable net system. So again, working closely with them to make sure we knew exactly what the weights were. And that's what we ended up with. It just gives you a feel for obviously drawings and generated model. A few facts, before I pass over to Chris. The whole total roof area is just under 50,000 square metres, so it's big. It's a total weight of steel for around 6,000 tonnes. Under the worst case snow loads, you might expect the front of the roof to deflect by around 400 millimetres, which is, it's for this kind of structure, dynamic structure, it's going to be around that. And this is the kind of natural frequency that we're getting the lowest, and that's obviously a long way below what we'd all like to be under normal conditions. And I suppose before I pass on, it's just reminding ourselves that this is where we've come from. We've come from an Olympic stadium with a roof that covered, maybe half the upper tier, a little bit more, extended to cover all the seats as they were, and then the final push, which pushed us to be that little bit different in the way we thought about things, that covers all the seats, and so suddenly becomes a real Premiership football ground that keeps West Ham happy and can also run athletics. At which point, I think it's time that I passed over to Chris and let him talk you through some of the construction. But I will see if I make sure I can pass over to the right. There you go.
Okay, thanks, Tim. So I work for Flint & Neal, and we were working alongside Bureau Happold. We were working for Balfour Beatty, the main contractor, carrying out the erection engineering. And as Tim's talked through, this is really the way we started. This is the story that we're telling. And this also is how my presentation will be broken down into three main parts. The first thing is how did we deconstruct the original stadium, shown in red there. The second part is how did we strengthen the structure that was retained, so that was the compression truss and the V-columns. And then finally, how did we actually get the big new roof up in the air. We got involved around about June of 2013, which was after Bureau Happold and Populous had developed a design to stage E. At that point, Balfour Beatty went through a competitive tendering process and were awarded the design and build contract by the London Legacy Development Corporation to take the project through construction. Bureau Happold and Populous were retained by Balfour Beatty as permanent works designers, and we came on board to help with the erection engineering aspects. The main subcontractors for Balfour Beatty at this point were Pfeiffer, who did the cable supply and installation works, William Hares, who did the steelwork, and Lakesmere, who did the cladding. And this is broadly what the construction program looked like. This is actually the final construction program, and the red line on the right-hand side shows where we are now. Contract was awarded in June 2013. Then we went into a short period of detailed design and affordability review, where the design went through another couple of iterations to bring the contractor's price within the client's budget. In parallel with that, we started unbuilding the existing stadium roof. That took us 3 months to do, followed by 7 months of strengthening, and the total program for the construction of the new roof was just 9 months. So the first part of my presentation then is about deconstruction. How do we take down the old roof from the stadium? And there are three key elements to it. The first is taking down the old iconic steel lighting towers, the A-frame lighting towers. Second thing is taking down the stressed fabric membrane, and finally lowering the cable net. And this is a view of where we started. And you can see on top here, this is the first thing that we had to deal with, taking down these lighting towers. 14 of them arranged on top of the existing tension ring, all linked together, and each one weighing around about 40 tons. The load path for the stability of these structures, you've got the red backstays at the back, which are stopping them from falling inwards, and then they're all connected together by a large circumferential cable which prevents them from falling backwards. Obviously, the circumferential cable means that we can't then take them down one by one because they're all connected together. So the first thing we had to do was replace that with a series of cables that spanned across the entire stadium. So we had a sort of bicycle wheel going across the stadium, which linked the lighting towers in pairs. and all the cables came to a central node at the point. And so the lighting towers are now linked together in pairs. We had a pair of crawler cranes, 600-ton crawler cranes, servicing that, and they worked in tandem to lift down the A-frames in pairs. Once the crane had got hold and stabilised the lighting tower, the cross cables were removed, and then the lighting tower can be lifted off and down to ground. The sequence was then developed and analysed in the analytical model, and we tried to keep the distribution of load as even as possible throughout the process. The crawler cranes tracking backwards and forwards, using the space that they create and lifting down the lighting towers in pairs. And there they are all on the ground. The next part was relatively straightforward, taking down the stressed fabric membrane, and this is supported by a secondary cable net structure above it. It worked on two construction fronts, de-stressed the cables that were supporting the fabric membrane and cut them away bay by bay. The fabric was, this shows just one bay, the fabric was brought forward to the front and lowered down by a series of winches down into the field of play. The fabric was taken away somewhere to the south of France, I think, and recycled. Once all the membrane's off, we're then left with a primary cable net structure. This consists of the tension ring shown in yellow, which is a bundle of 8 lock coil strands, and that's supported from suspension cables shown in green and stressed by the lower radial cables in blue. And the process here was sort of the opposite of the way that it was lifted in the first place, but we did something fundamentally different towards the end, which I'll come on to. The first job was to fit strand jacks to the ends of each of those blue suspension cables, which allowed us to then lengthen that upper radial cable by feeding through temporary strand through the strand jacks. We lengthened the upper radial cable until the lower cable went slack, and this happened at a different point for each cable in the structure. As soon as that lower cable went slack, we then had to remove it, because if we carried on lowering it, it would have gone tight again. This view just shows there's the jacks in place, starting to lower the cable net. And here's another view. The jack is here, hydraulic jack in its jacking frame. This is the temporary strand coming out of the back. Tension ring in yellow. And the landing areas for the jacks, very simple polystyrene blocks, minimizing the temporary works we were using. And we were removing small areas of seating. One of our jobs in the analysis model was actually to predict very accurately where these jacks would land, and make sure we had the polystyrene blocks in the right place. The big challenge, though, with lowering the tension ring was that the seating of the existing stadium was immediately below the tension ring. And if we had simply lowered it vertically, we would have draped ourselves over the upper tier of seating. And because the upper tier of seating is shown in blue here, because it's coming in and out with the geometry of the seating tiers, if we'd have done that, the tension ring would have draped itself over the various parts of the upper tier of seating. And we would have needed to install large amounts of scaffolding in these areas to support the tension ring as it came down. Clearly, the contractor wanted to minimize the cost and temporary works involved in this process. So we came up with another solution, which was to install another set of cross cables across the stadium, shown in blue here, so that we were able actually not only to lower the tension ring, but to pull it in. And by pulling it in, we could clear all the seating tiers and lower it down onto the field of play. So this is what the structure, this is a view from our analysis model, this is what the structure looked like once we'd installed all of those brace cables. And here they are, here's a view, these crossed cables. They're linking opposite sides of the tension ring, here are the tension ring nodes. Clearly we have to be able to shorten those cables as we're lowering the tension ring. So the cross cable comes into a pulley block as it approaches the tension ring. There's then a sheath before the cross cable goes through a block, the tension ring, and down to a ballasted winch drum on the field of play. And by using these winches, we're able to control the lengths of these cross cables. The cross cable shown in red there. And so this is what the lowering of the tension ring looks like. It starts to come down. At various points in time, we remove the lower radial cables. before we hit the upper tiers of seating, we install these cross-bracing cables, and then we start to draw in the tension ring, scoop it up, and by simultaneously shortening those cross-bracing cables at the same time as we're lowering the cable, we can control where it ends up. So that was the deconstruction of the existing stadium. We then went through a period of time where we carried out strengthening works. This included the replacement of all of the V-columns around the outside of the stadium to put in larger cross-section sizes to deal with the increased vertical loads. And also there was a lot of scaffolding that went up around the compression truss to deal with, to provide shelter for the welding activities that were necessary to strengthen the connections. The new roof then was built in in three parts. The first part was putting the new cable net in. Then we erected the rear roof structure. And finally we erected the front roof. And these were dealt with as three consecutive periods in the construction process. Tim's already run through the design, but I'll just quickly draw out some pertinent points here. There's the cable net in blue. The cable net has a tension ring at the front here, but it has an intermediate cable net node here, which supports both the rear roof on the V-struts coming down and supported off this intermediate node, but also the front roof, which consists of this lighting tower, the radial front rafter beams, and the cross bracing. That's also supported both off the intermediate cable net node here, as well as off the tension ring. So we have, if you like, two independent structures. The structure at the back, which is formed of these triangular modules, is articulated in the sense that each module is able to move independently of the other. So it can absorb deflections in the cable net without setting up any parasitic stresses between the different modules. The front roof, as Tim has already explained, is different. The front roof has these continuous rings, compression rings, which run all the way around the stadium, and they're cross-braced with this cross-bracing here, so that the whole of the front roof is a continuous structure around the whole of the stadium. So it is able to, it stiffens up the response to the cable net, but it also means that it picks up secondary stresses as the cable net moves. And that's a view shortly after we'd finished erection of the front roof, which really just shows you the complexity of the steelwork that we're building on top of this cable net. So the first part of construction, building the cable net. The first job here was to come up with a geometry that we could lay out the cable net in the field of play. It was much easier to place the tension ring this time around because it was that much closer in. We had to cover all the seats, so the tension ring was much closer into the field of play. The difficulty here now was where did the elements that form that intermediate cable net node sit? Because now we were in a situation where this node here is sometimes on the seating, sometimes off the seating, and in a lot of places it was very awkwardly ending up just off the upper tier of seating. So when we lifted the cable net, we would have had to have dragged this steel node up and over the seating tiers, which is difficult. It would have damaged the seating tiers, and it would have been really quite awkward. So the first challenge was to come up with a geometry that we could lay out the cable net in as a starting position for developing a jacking sequence that we would lift the cable net with. This view shows the tension ring being laid out, and we actually shifted both the shape of the cable net, but we also shifted the whole tension ring to the east, which allowed us to place these intermediate cable net nodes just on the edge of the upper tier of seating here. And on this side of the stadium, just out of view, they're actually on the ground. So we simplified things, and we said they're either sat on the upper tier of seating or they are some way from it. They aren't in that awkward middle ground. It made the jacking sequence more complicated, though, because a large part of the jacking operation involved then changing the shape of the cable net as we were lifting it. This is a view of the tension ring on the ground. Brings some of the scale to unfortunately there isn't someone stood next to it, but these are very large steel elements, and the tension ring is formed of these 8 lock coil strands. This is a view. Here's the tension ring elements, and here are the intermediate cable net lugs, which are perched on the end of the upper tier. And I'm pleased to say they were restrained back with temporary turfers. They didn't come shooting off the edge. But again, temporary works, very, very simple, polystyrene blocks, and just local removal of seating. So, the first part of the lift of the cable net is to lift the cable net. And the way we did that was to place temporary strand jacks on the top chord of the compression truss up here, and use temporary strand going from that jack down and fixed to the end of the upper radial cable. This view here shows, here's the strand jack mounted onto the top of the compression truss, the temporary strand and clamped to the end of the permanent cable. The strand is then shortened. The strand jacks, there are 56 of them. They're all linked together, hydraulically linked, back to a computer system run by VSL in the center of the stadium. We've given VSL our jacking sequence in a spreadsheet form, and they've entered it directly into their computer. So they can then press a button and work through our jacking stages one by one. The jacks pull about 300 millimeters of strand each time in a predefined sequence, which we've defined. And this view shows you the situation as we're getting towards the end of the lift on a particular grid line. Here's the jack, here's the clamp, and the final operation to fit the pin is done by hand. Another view showing a few of the strand jacks. So, once we have finished the jacking operation, we fit the pins at the top, and the next job then, having the lift being complete, is to install these lower radial cables. That's done by winching in against the bottom chord until we can get close enough to fit the jacks. This slide here just shows you a view from our analysis model of the lift. And you can see the first thing it's doing is the tension ring is changing shape and sliding along the ground. Once all the lug plates are up, we can lift freely. Okay, that's the stressing. So that's the tensioning of the lower radial cable there, and that's done using. Once we get close enough with the lower radial cable, using the winch, we're then able to connect it up to these threaded rods with jacks and jack the final part of the distance that we need to move. This was done on 4 construction fronts, working simultaneously and working their way around the stadium. With those cables stressed, the tension ring here is now about 2 to 2.5 meters above its final position. It's got no vertical load on it from the steelwork, so it's quite substantially higher than it will be in the final construction. If we were then to start building the steelwork on top of it, you can imagine that we would have 2 to 2.5 meters of movement when we were building a steelwork. The effect of that would be that none of the steelwork would fit as we were putting it together, and the steelwork contractor would be forever on the phone. So what we did here was to tie down the tension ring. So every other of the tension ring nodes was tied down by a series of temporary tie downs to a large Kentridge block in the field of play. And we tied it down to a position just above its final geometry. So we were able to tie it down by about those 2 meters, pull it down. The Kentridge blocks, quite basic. Each one's 135 tons of soil and manhole rings and concrete blocks. And it was tied, the 2 meters were tied down by going around the stadium in 7 laps, sequentially lowering the tension ring step by step to do it in a uniform way. We weren't able to simply pull down on one grid line by 2 meters and then go to the next one, because if we pulled down on 2 meters there, these two here would have flown up in the air. So we had to come up with a sequence that allowed us to do it gradually. All through this process, we're monitoring the forces in the cables, we're monitoring the forces in the jacks that we're doing. I've got a couple of slides that just shows you where we ended up. The orange is VSL, that's the contractor, that's the jack, that's the force on the jack, and the blue is the number from our analysis model. These are the forces in the cables during the lifting stage. And these are the forces in those lower radial cables during stressing. And then finally, This is the comparison with the tie-down forces after we've finished the tie-down. Now, all of this cable net erection is done to a geometry, not to force. So there are differences in the forces which correspond to different stiffnesses in the structure. But it was a fairly reassuring match. I've now just got a couple of slides which show the cable net going up, stressing, and then the tying down. That goes a lot slower on my machine. And there, the FIFA team having done a very good job set on the cable net, having a team photo. So once the cable net was up, the next job was to build the rear roof structure. This was relatively straightforward because the articulation of the rear roof means that each module is independent of the others. And so they were erected by 3 cranes working on 2 different construction fronts. And again, this is from our analysis model. Module by module, 3 cranes on each construction front, and I'll go into detail as to what each crane was doing. But the whole of the rear roof was erected before we started anything else. So the first thing to do was to place the first back diagonal beam together with its corresponding strut that sits on the intermediate cable net node. That was then held from the first crane, whilst the second crane came in and did the same thing on the other side. The pin connection is made and the 2 beams are bolted together at the end. A third crane comes along, places some temporary bracing in between the 2, so that when crane 1 and 2 release their load, the structure is stable. That's then repeated for the next module, and it looks something like that. After that's done, the rest of the cross bracing and super purlins are placed between the back diagonal beams before we infill with these infill purlins. Now, these infill purlins have slotted holes at the end, so they are sliding details to allow those different rear roof modules to move independently of one another. And that's a shot with the first 4 up. That progressed all the way around the stadium quite smoothly before we come to the front roof, which is a slightly more complicated affair. Just as a recap, the front roof consists of this lighting tower at the front, which is inclined in towards the field of play. It contains the lights and the PAVA equipment for the stadium. That's held in place by three of these front radial beams, and those are propped off the tension ring front and back through A-struts. Those radial beams then joined all together with these continuous hoops and the cross bracing to form the diaphragm action. Now, obviously, when you're building a structure like this, the fit-up becomes that much more complicated compared to building this structure, which is much more tolerant of movements. But we did it in the same way. We built them up as discrete lighting tower modules, again working on 2 construction fronts, 3 cranes on each, building a lighting tower and then coming back and infilling the purlin back to the adjacent towers. All of this analysis was done on LUSAS, which is a finite element package, and we had LUSAS finite element analysis company helping us do this, but also they were carrying out a category 2 check for us of our analysis. So, as I alluded to, the difficulty with building the front roof is that you have these continuous rings which form secondary compression rings in the structure, and they're intended to be under compression in the permanent condition. So the completed structure has a permanent level of compression in these members. Effectively, they are pre-stressed by the cable net. So there's a challenge there. How do you get that compression into those members during the construction process? This slide, I hope, tries to explain that. The blue lines show you the geometry of the cable net after we've finished building the rear roof. So the cable net's tied down, the tension ring is at its final level, but the intermediate cable net node is high. So were we to build the front roof in that condition, the front roof would be pitched forward of its final geometry. That means that because these radial beams are inclined towards one another, that if we tried to fit the circumferential members between these beams, they would be too long and we wouldn't be able to fit them in. So our first job was to pull back the front roof somehow. And in pulling it back, we would push down this node and generate the pre-stress effect. The way we decided to do that, and we would pull it back into its final geometry so that then the members could be fitted in. The way we decided to do that was by a jack which connected the front of the back roof to the back of the front roof. So this gap between these two structures, we placed a jack on every grid line. And we during the installation of each lighting tower, we would jack it back, and we would leave the jacks. We would jack it back to a predefined geometry, which came out of the analysis model, and then we would leave those jacks in place until the front roof was complete, and then we would go through a staged process of de-stressing them. This slide is from the Steelwork Fabricators Tekla model, and it shows you the detail, the jacking detail that we used. This here is one of those front radial beams. You're standing at the compression truss looking towards the center of the stadium. There's the front radial beam. This is the triangular rear roof structure here, and then this is the link post detail that is a temporary structure to connect the two. You have the jacking bar, which is the middle bar there, with a jack arranged, and two bars either side of it, so that jack could be used to pull back this front rafter, set it to length, and then the jack could be taken off and used on the adjacent modules, leaving these two bars to do the work in the meantime. And this is a view stood from the top of the roof. Again, from the compression truss looking out, here's the rear roof with the cladding in place. Here's the upper radial cable going through the rear roof, and here's the front roof structure. These are the guys from Hares who are operating the jacks. This is the module being erected. And so you have a link post jack, what we call a link post jack, on each grid line. This, I hope, will... Well, yeah. So this is a displacement of the structure as it's being built. You can see as we're building the rear roof modules one by one, the cable net is moving, pushing, if you like, a wave in front of it. We finish the rear roof structure, then we start building the front roof. And you can see the amount of jacking that's done to pull that lighting tower module back and to pre-stress it into place to allow those circumferential members to fit. And you just hope the last one fits. Okay, this is the same sequence, but it shows you the force. So this is showing. Okay, I might not be able to show you that. Oh, yes, I can. Okay. So it's a plan view. If the member is orange or yellow, it demonstrates that we're able to install the members under zero force. So you can see we're installing all the members under zero force as we go around because we're able to jack them back into the right geometry first. When we get to the end, there's then a sequence of de-stressing those jacks, and that introduces the compression force into the members. And you'll see there, that's when we detension those jacks, and those now complete rings go into compression. Okay, briefly, some more detail on how we erected the front roof. So the tower went up. The tower was lifted, prefabricated on the field of play and lifted by a single crane. This is the first one going up. So that's lifted by one of these 600-ton crawler cranes and placed onto the tension ring. The pin connection's made at the base here. And we then come back with a second crane and we install these two supporting struts either side. And there's the first one going in. Once the lighting tower and the supporting struts are in place, we can then lift in these radial beams. This part of the structure is still being held by the first crane to prevent it from falling into the field of play. The second crane is then installing these rafter beams. once we have those, and there's a picture of one of the rafter beams being lifted. Once we have those rafter beams in place, they act then to prevent the lighting tower from falling in. So the structure is stable in this condition, in still air conditions, which the contractor was able to control on site. So at this point, the crane can then release the lighting tower. This is installing the intermediate rafter beam. You have to have a head for heights for this. So once the three radial beams are in place, then the crane can then come back and infill the cross bracing, and that cross bracing has to be installed inside a shift, so that we're able to leave this structure stable, subject to wind loads overnight or before the next shift starts. And that's a view of the first one. That process is then repeated for the next one before we come back and infill in between. Now, it's the infilling in between that's the most difficult operation to do, because you're building a steelwork structure onto a very flexible cable net. And with the best will in the world, you have a lot of construction tolerance to deal with in terms of exactly where these two steel structures are going to end up. So you don't know what the gap between that is to a very high level of accuracy. So the way we didn't want to adjust the lengths of any of the members, so the way that we dealt with that was to use the tie downs to give us some adjustability. So remember that the tension ring is tied down at each of these nodes. And if we wanted to increase the size of this gap, we could simply use the tie downs to do that for us. So we had Pfeiffer. Pfeiffer stayed on site, and they helped Hares with any fit-up issues that occurred. We developed some strategies for how to do that. And for example, in this simple case here, where we want to increase the gap, rather than change the length of the member that we're trying to place in there, we slacken off this tie down here, and we pull down harder on these two. And you can see that has the effect of opening that gap. The opposite is true. If we were to pull down on this one, slacken off on these, we could close the gap. So by doing that, the contractor got pretty fast, pretty efficient at doing it and fitting up the steelwork. And by doing that, we were able actually to install all those members at their nominal lengths, so without any adjustment at all. I think 2 members out of all of this steelwork had to be adjusted on site by about 30 millimeters. But otherwise everything went to length, which was quite an achievement both for the steelwork fabricator and the cable erector. And that's what it looks like this week. I've got a final couple of slides to show you where we ended up in terms of geometry against where we predicted we would end up. The cable net structure is a very flexible structure, and we've got a long span structure, so we're not dealing with the usual tolerances that we deal with for normal steel structures. B.R. Happold had developed some guidance on tolerance, which they had made allowances for within their design, and we were aiming to achieve those. So throughout the whole of the front roof erection, we were doing surveying with traditional surveying methods in the field of play, and we were monitoring retro targets at each of these points, A, B, C, D, E, F, and G, to look at both to control the jacking operation, so that we were able to make sure we were jacking it into the right place, but also to check that we were ending up in the right place. So if we look at where we ended up on the tension ring, this is point E, so this is down here. Compared to where we predicted we would be right at the start of the project, and taking into account all variabilities on the permanent load, which Tim alluded to in terms of the control and the effort that went in to control that permanent load. A lot of the steelwork members were weighed on the crane before they were placed on the structure. We ended up within plus minus 30 millimeters of where we should be. The intermediate cable net node, this is probably the most flexible part of the structure because it has no stiffness, has no lateral stiffness, and it has a limited amount of vertical stiffness that it gets from the cable net. The tolerances here, as a result, were higher, so that we were told to aim for plus 100 or minus 25. And the red line shows where we ended up. the vast majority within tolerance, I think that's a total of 5, drifted slightly out. And then H is the leading edge of this is the, if you like, the important one for the architect, the visual appearance of the structure. And vertically, again, the grey is the tolerance envelope and the red is where we ended up. So we're generally within 100 millimeters of vertical level on that. And it's worth just to put some perspective on that. This is the tension ring. You can see the 8 cables that form the tension ring there. Each of those cables is 100 millimeters in diameter. So, and that I think is my last slide. That's a view taken this week of the stadium inside. They've just lifted up the crane mat, which was forming the running track for the cranes as they were going around. And everyone had crossed their fingers through the entire construction process to make sure the track was still okay underneath. So when we lifted it up, there was a lot of sighing when it all came up okay. The first event in the stadium is on the 24th of July, when we're having the anniversary games. Thank you very much.